Hello everyone, I am Sriram from 3rd year EC department. In this video, we will discuss about design steps involved in designing of analog type 1 Chebyshev low pass filter. Let us see what does a filter mean. In signal processing perspective, filter is a device which removes undesired components from a signal. Filters that allow low frequency signals to pass through them and attenuate the high frequency signals are known as low pass filters. Analog filters are basic building blocks of all types of filters in electronics. Some well-known analog filters are Butterworth filters, Chebyshev filters, bezels and Gaussian filters. In this video, our area of interest is about Chebyshev filters. Chebyshev filters have smaller transition region compared to same order Butterworth filter at an expense of ripples in their passband and slightly degraded transient response. Chebyshev filters are classified into two types, Type 1 and Type 2. Type 1 filters have ripples in their passband, whereas Type 2 Chebyshev filters have ripples in their stopband. Mathematical characteristics of these filters are derived from Chebyshev polynomials. Chebyshev filters have a property that they minimize the error between idealized and the actual filter. The frequency response of Type 1 and Type 2 Chebyshev filter is as follows. Now let us see some properties of Chebyshev filters. Chebyshev filters have 0 dB relative attenuation at DC. Odd order Chebyshev filters have an attenuation band that extends from 0 dB to the ripple value, where ripple value is equals to 1 by root over 1 plus epsilon square. Even order Chebyshev filters have a gain equal to the passband ripple, that is, the gain vary between 1 to 1 by root over 1 plus epsilon square. The number of cycles of the ripple in the passband is equals to the order of the filter. Chebyshev Type 1 low pass filter. In Chebyshev Type 1 low pass filters, we have ripples in the passband and show monotonic behavior in the stopband. Type 1 filters are also known as all-pole filters. Squared magnitude response of the filter is given by h of j omega whole square is equals to 1 by 1 plus epsilon square cn square omega by omega p, where cn omega by omega p is Chebyshev polynomial of order n, and epsilon is the ripple parameter in the passband. The following figure shows the magnitude response of Type 1 Chebyshev low pass filter. Now let us see the steps involved in filter design. To start with, we must have omega p and omega s to compute epsilon, order of the filter n, and the pole locations to calculate the transfer function. Step 1. Calculation of the passband ripple parameter epsilon. To calculate the ripple parameter, we use the following expression, where epsilon is equals to 10 power 0.1 kp in dB minus 1 whole power 1 by 2, where kp is the attenuation in passband. In step 2, we calculate the order of the filter. To calculate the order of the filter, we use the following expression, where n1 is equals to cos h inverse 10 power 0.1 ks minus 1 by 10 power 0.1 kp minus 1 whole power 1 by 2 whole divided by cos h inverse omega s by omega p, where ks and kp are the attenuation in pass and stop bands respectively, and omega s and omega p are the stop band and pass band edge frequencies. The order of the filter n is equals to the seal value of n1. Step 3 involves the calculation of the poles. The poles of Chebyshev filter can be determined by moving the poles of the Butterworth filter to the right, forming an ellipse. On the ellipse, the coordinate xk and yk are given by xk is equals to small r cos theta k and yk is equals to capital R sin theta k, where theta k is given by pi by 2 plus 2k plus 1 pi by 2n. K extends from 0 to n minus 1. R represents the minor axis of the ellipse given by R is equals to omega p beta square minus 1 by 2 beta. Capital R represents the major axis of the ellipse and is given by capital R is equals to omega p beta square plus 1 by 2 beta. Here beta is the parameter which is given by root over 1 plus epsilon square plus 1 by epsilon whole power 1 by n. Here n is the order of the filter. The pole positions are given by Sp is equals to small r cos theta k plus capital R sin theta k. The various values of theta k are computed before and are substituted to form the poles. Step 4 is the calculation of the system transfer function. The system transfer function h of s of an analog filter is given by h of s is equals to k by s minus s naught, s minus s1 and so on. Here s naught, s1, s2 are the poles which are calculated in the previous step. Value of the k can be calculated as follows. K is equals to b naught when n is odd and k is equals to b naught by root over 1 plus epsilon square when n is even. B naught is the constant term in the denominator which is formed by multiplying all the poles. Now let us see an example. In the problem we are given with omega s is equals to 50 radians per second, omega p is equals to 20 radians per second, ks and kp are 30 and 2.5 dB respectively. Upon substituting value of kp in the epsilon expression, we get epsilon is equals to 0.882. Now we calculate order of the filter by substituting the values in the following expression. After substituting, we get n1 is equals to 2.729. The order of the filter n is equals to Ceil value of n1 where n is equals to 3. Now we calculate the values of theta k by substituting k is equals to 0, 1 and 2. The minor axis of the ellipse is 6.6 and major axis is equals to 21.06. The expression of the poles are as given below. Now we multiply the poles together to form the denominator and the value of k is directly evaluated by multiplying the constant value of the poles as n is 3. So we obtain a transfer function where h of s is equals to 2265.27 divided by s plus 6.6 into s plus 3.3 plus j 18.3 into s plus 3.3 minus j 18.23. Thank you.